Welcome to Nuclear Matters from the Australian National University College of Systems and Society. I'm your host, Liz Williams, a nuclear physicist and nuclear systems discipline lead for the ANU School of Engineering. In today's episode, we explore how nuclear technologies play a role in enabling life-saving cancer treatments. Our guest, Eva Bezak, is Professor of Medical Radiation at the University of South Australia and President of Asia-Oceania Federation of Organizations for Medical Physics. I've asked Eva to join me today to find out more about how nuclear technologies for medical applications get developed and used to treat patients across Australia. To get us started, I asked Eva to give us a sense of how many people's lives are likely to be touched by cancer.
Cancer would be, one of the number one diseases in the country that will be affecting 1 in 3 to 1 in 2 Australians in their lifespan, especially since we are living longer. And we have a couple of main sources of therapies, which is, of course, surgery, chemotherapy, immunotherapy, but not least radiation therapy, where we're using primarily radiation X-rays produced by medical linear accelerators or photons to deliver energy to cancer and causing enough cell damage to eradicate the cancer cells. Radiotherapy is actually extremely effective in treatment of localized cancer in particular, and should be used for the treatment of about 50% of cancer patients, and the local control of the disease where the primary tumor is, it is as effective as surgery. So it actually represents a very cost-effective as well as treatment-effective therapy. Where the radiotherapy has maybe disadvantage is when the disease spreads, and then we need to look at something like chemotherapy.
So in many cases, radiation therapy is a really useful treatment. And what you're doing is using a linear accelerator to generate X-rays that you can then use to kill cancer cells. I want to understand how this kind of treatment is delivered in hospitals. So can you tell me what it's like to be involved in this kind of treatment from a clinician's perspective?
Absolutely. So the day of a medical physicist is varied. Sometimes it can start early in the morning because before a first patient comes to the department, all the equipment, including accelerators, CT scanners, data servers need to be turned on. And in the morning, some initial quality assurance is performed.
Right.
So what I usually teach the student that radiotherapy is a double-blind date. You don't see the tumor and you don't see the radiation, yet you want to deliver that radiation with utmost precision and accuracy to the target volume. Yeah. Because radiation is also detrimental to a degree to healthy tissues. And if you miss the cancer, then you might be giving unwanted amount of radiations to the healthy tissues, causing negative side effects. So when the therapists turn on the machine, they want to ensure that the right amount of radiation is coming in the right direction. And they trust medical physicists that we have done all the necessary testing and quality assurance measurements to ensure that the therapist can absolutely rely on the linear accelerator to perform its task.
Okay.
So often we are the people behind calibrating and testing the accelerator and its performance.
Okay. So let's just talk through this in kind of a step-by-step fashion.
Sure.
Let's say you have a tumor, you kind of know, at least based on imaging, where it is, how large it is, where it sits in the patient's body, right? We're starting with a scenario like that. And so for radiation therapy, you would want the linear accelerator to produce the radiation you need and the intensity that you need, the shape that you need, right?
Absolutely.
To irradiate the tumor, but as much as possible to avoid the the healthy tissue surrounding. So the calibrations that you're talking about, the quality assurance, it's all about ensuring that you have very high level of understanding about what radiation the machine is producing, what shapes, it's irradiating, that kind of thing. Is that about right?
Yes. In order to irradiate the tumor, we need to understand the linear accelerator. When the X-rays are produced, the treatment head sits on the rotating gantry.
Mm-hmm.
That gantry weighs around 6 tons, 3 Commodores, or I should call it 3 Fords, since we no longer produce holders in the country. And it rotates around the patient with the accuracy of about 2 millimeters.
Right.
Part of those checks are also mechanical checks, as well as radiation checks. But before the patient even gets onto the linear accelerator, we need to perform the dose calculations on the CT image of a patient. So we call that treatment planning.
Yeah.
So in addition to just, the patient doesn't just come and is like positioned on the patient couch to deliver the treatment. There is this big preparation period when we acquire a CT, three-dimensional CT image of the patient,
mm-hmm.
where we outline the target volume and the shape of the target volume. And we also outline the surrounding healthy tissues, which
Right.
are also called organs at risk or critical structures.
Okay.
And then we use very sophisticated treatment planning, dose calculation algorithms that allow us to optimize the intensity and direction of the radiation from the linear accelerator gantry. For example, we will not irradiate through spinal cord.
Yeah, okay. Well, I'm assuming that causes lots of problems.
Absolutely, yeah. So only when we have pre-calculated how the dose should be delivered, and the clinician improves the dose calculation and dose distribution, that will be then transferred online digitally to the linear accelerator, and then that treatment can be delivered. I was also talking about that, we don't see the tumor.
Yeah.
Our modern linear accelerator have additional robotic arms that have an additional X-ray tube and imaging detector attached, so that just before the treatment, we can take a snapshot of the patient anatomy and have a sneak peek where that target volume is just before the treatment fraction, adjust the position, and then deliver the radiation according to the treatment plan.
Mm-hmm.
And again, physicists are involved in calibration and testing of the CT simulator. We designed the radiation beam models inside that dose calculation software.
Yep.
And we also look after that imaging equipment on the linear accelerator.
Okay.
To ensure that we get, true fidelity images. And when we adjust the position, we are moving the patient in the right direction.
Yeah. I don't know if you can answer this question, but what is this like as a patient? I mean, I imagine you have to stay very, very still.
Yeah. So as soon as the patient and the families hear the C word, it's one of the most scary events in their lives. So before a patient actually starts therapy, they will be explained what's going to happen during the process. Mm-hmm. And they might even have a visit to the department prior to their commencing the treatment, so they can visualize the accelerator, the couch, and the process. I do think that it can be quite overwhelming. Yes, they have to hold their position once they are in therapy for a few minutes, mm-hmm. but the patient does not really feel and see the radiation, they can definitely see the gantry moving around them. Mm-hmm. What we see throughout the process, because the radiotherapy is not delivered in one treatment fraction, it's delivered in multiple treatment fractions, that once they are used to the system, they start relaxing a bit and it changes their body posture sometimes. Right. But that's why we have that imaging, so that we can always adjust them appropriately to identify the target. If I can go to physics a bit, and I'll start with a controversial statement. X-rays are actually very silly ionizing radiation to be used for radiotherapy. The reason being that the X-rays attenuate exponentially through the medium, including through the patient's body. And if the listeners can imagine the exponential curve, you will have a high dose of radiation somewhere at the surface, closer to the surface of the body. Mm-hmm. Then you will be delivering lower dose of radiation, perhaps to your cancer. Let's say it's prostate in the middle of the pelvis. But because the exponential curve never reaches the x-axis, you will always have radiation also exiting the patient.
Right.
So potentially we're giving a dose before the tumor and after tumor.
Right.
And the only way we can resolve this problem, and this is where the rotating gantry comes into place, that we can never ever use a single radiation beam on radiation direction. Yeah. And we cheat a bit. We irradiate the patient from multiple beams, sometimes even in a 180-degree arc or more, so that all those beams meet in the target volume in the cancer where they build up the dose.
Yeah.
And we spread that unwanted dose around the larger volume of healthy tissues.
Let's try and unpack that a little bit for our listeners. So basically what you have is a very high dose at the start, and that drops off very quickly, again, an exponential. If you don't know what that's like, it's almost like a skateboard ramp. You're
exactly
rolling down to the bottom of this well, and that skateboard ramp, it's only one-sided, and it keeps going and going and going. So you can imagine the dose getting lower and lower and lower, but never reaching zero.
Exactly.
Okay. And so if you are rotating that skateboard ramp dose, I don't know if that is a helpful image, around, you are basically distributing the dose that you don't want throughout healthy tissue. So it has a higher chance of being able to repair back to normal.
So if you think about, again, prostate cancer, which is sort of one of the most common cancers around the world, if you treat, let's say, through bladder, then we would be giving much higher dose when using a single beam to the bladder rather than to the prostate. So if we are rotating the skateboard ramp around the patient, then we will maybe, redistribute that dose through other pelvic organs, maybe including rectum, including kidneys, including muscle, including pelvic bones. But small amount of radiation to healthy tissues is better because healthy tissues can repair it than giving large amount of radiation to healthy tissues in order to reach the target volume that the cancer is.
It's maybe worth noting that we humans have evolved in an environment where there is natural background radiation.
Absolutely.
Our body has a way of dealing with some reasonable level of radiation.
So patients often ask me, if radiation is so detrimental, why can we use it for treatment of cancer? And the reason is that the cancer cells behave slightly differently or much differently to the normal cells. And cancer cells have also perturbed repair mechanisms. So they are much more radiosensitive or susceptible to radiation damage than normal cells. So if we give a small amount of radiation dose, it can kill a cancer cell. The normal cells will have some radiation damage, but they can repair it. And this is really why, by large, we are not doing radiotherapy in a single day.
Yep.
be fractionated. So we're giving the 24 hours for normal tissues to repair the damage before we irradiate the patient again and keep accumulating the radiation damage in the cancer. So the differential effect comes in different responses of cancer to the radiation damage versus normal tissues. But having said that, that treatment planning that I spoke about in the beginning is one of the most important aspects of radiotherapy, where we are really investigating that we are not giving unnecessary dose to any of the surrounding healthy tissues.
Yeah. Well, you started out this discussion about this type of radiotherapy with a controversial statement. I'm wondering what alternatives there are.
So the problem is that no matter how much you improve the linear accelerator for photons technology, how much you improve treatment planning algorithms, you can't change the physics of photons, and they will always attenuate exponentially. So there is a limit to your improvements, and you always will have an exit dose beyond the target volume. So in order to really overcome this conundrum, we have to move away from photons, from X-ray radiation. But this is where nature is saving us again, because charged particles such as protons or alpha particles or carbon ions deposit radiation dose inside a medium, which would be including patient bodies, completely differently. And I don't know how well to describe it for the listeners, but the dose deposition starts with fairly low dose plateau region. And most of the energy is deposited towards the end of the particle's path.
Yeah.
Particles actually have a finite trajectory, finite distance in the medium when they come to a complete stop.
Yep.
And most of their energy is deposited, about 80%, right at the end of their trajectory, generating very sharp peak of energy deposition.
Yeah.
And this peak is known as Bragg peak in the honor of the scientist who discovered it. The funny things about this Bragg peak also is that the position or the distance that the particle travels into the medium depends on the energy of the particle. So if I have a lower energy particle, that Bragg peak can happen at 2 centimeters into the body. If I select another energy, it will be 5 centimeters in the body. If I have a target volume like prostate in 20 centimeters in the body, then I will select appropriate energy of a charged particle, such as proton, and the bulk of that energy will be deposited exactly in the prostate target volume.
Okay.
Which means that now I have lower doses before the target volume, and I have 0 doses behind the target volume.
Right.
So I have minimized the entrance dose, maximized the bulk of the energy, bulk of the radiation dose in the target volume, and I have removed the exit dose.
Right. So basically, you
ideal.
Yeah. So you basically have a scenario where that tumor, you can target it very directly by adjusting the energy of the charged particles that you're using for treatment. So maybe one way we can help people think about this is when you are, let's say you're throwing a ball into water, right? And if you are throwing a ball that's, heavy and really fast, it's going to take a little while to slow down, right? But if you are throwing a lighter ball with that you're throwing it slower, it's going to slow down or stop in that water much faster.
Yeah. Yes. But, it's from what the objective of radiotherapy is. Charged particles are ideal because it does give you that differentiation between accumulating high levels of doses in cancer while minimizing the doses in healthy tissues.
Yeah.
So that's really what we want to achieve. So you might then ask, if charged particles are so good, why aren't we using charged particle accelerators?
I was just going to get to, I know you've been doing some work on this. So what do you think about this?
Photons are also what we call sparsely ionizing radiation. So they are not depositing the energy very intensely.
Mm-hmm.
However, the charged particles is something that we call the dense ionizing radiation. That means that they are depositing much more energy along their trajectory.
Yeah.
So while I can have 18 MeV beam photons to reach the prostate at 20 centimeters, I would need 200 MeV proton beam to get to the same depth inside a patient.
Wow.
So the energies we have actually increased by 1 order of magnitude. And if I move to carbon beams, I need about 3,000 MeV carbon beam. Mm-hmm. Because again, that energy loss, energy deposition of a carbon beam per unit per micrometer is much more intense, much more dense compared to photons. And because they are losing their energy so rapidly, we need to start with much higher energies to actually have any energy to deposit in the target volume. Mm-hmm. And so in order to start with protons of 200 MeV, going back to the protons, I need different accelerators.
Yeah. And much more powerful ones, I would imagine.
More powerful accelerators, larger accelerators. So this is increasing then demands on the technology, and it also increases demands on the footprint of the facility, mm-hmm. because you now need a much larger facility that needs to be shielded with the concrete bunker. Then once you get that beamline into the treatment room, once again, we want the gantry to be rotating around a patient, so that we can direct that radiation through the right body path length to reach what I call target volume or cancer. Mm. The gantry now weighs, I was telling you the linear accelerator was 6 tons. Now we can talk 100 tons, 200 tons.
Wow.
Or even the facility in Heidelberg in Germany, the gantry weighs 680 tons.
That's a major engineering project.
Absolutely. And a huge addition to the costs.
Yeah. I'd like to get into the health economics of these options a bit. So what's the cost of a linear accelerator facility like the ones we're using in hospitals across Australia right now versus the cost of the charged particle facilities we're talking about?
When we're treating patients with photons, the energy range of photon beams is from 6 MV to maybe 18 MV beams. And the accelerating structure is about 1 meter long. So you can put the whole accelerator in a single treatment room. And the cost of the modern day accelerator with all bells and whistles is $2 to $3 million. While I can maybe set up a linear accelerator facility with the bunker and everything, maybe for $5 million, you would need $50 million to set up a proton facility and maybe $200 million to set up a carbon facility.
Right.
What we know from photons, that, as I was telling you before, they are as effective for localized cancer as surgery. Mm-hmm. So we can still use photons for many cancers, and therefore not only every capital cities, but even in smaller cities, we now have cancer radiotherapy facilities in Dubbo or Wagga Wagga or south of Wollongong. Yeah. We can set them up regionally and enable the access of local people to standard radiotherapy. Yeah. With these expensive facilities, we potentially don't have to treat patients that already have fantastic outcomes with photons, but we will use it for specialized patients with cancer, where the protection of normal tissue is of utmost importance.
Mm-hmm.
So maybe we only need 1 to 5 such facilities in Australia,
Yep.
and make it a preferred treatment option, for example, for pediatric cancer patients.
Right.
Yes, so if I am irradiating, for example, a brain cancer in a 6-year-old patient and I'm using photons, we are very good at eradicating that brain tumor. But more likely, again, due to that exponential attenuation, I will include a bit of optical nerve, bit of ear canal, bit of brainstem, bit of pituitary gland.
Yeah.
And all of these then can impact on the well-being and development of the child, impaired vision, impaired hearing.
Mm-hmm.
Then they will have development and speech delays. There could be a bit of growth delay because we are also impacting some of the hormonal centers with the glands in the brain. So this is where something like protons are absolutely amazing.
Can I step back a bit?
Yes.
I'm curious, these kinds of facilities, as I understand it, this kind of treatment started out as being delivered or experimented with at research facilities. Is that right?
Oh, absolutely. Look, the Bragg pig was discovered 120 years ago.
Mm-hmm.
So the physics is not new. And I will make a bit of claim. Bragg pig was discovered at the University of Adelaide, here in Adelaide, while Sir William Henry Bragg was conducting the experiments here. It wasn't until we had accelerators in 40s and 50s of the last century that we could actually build the first nuclear physics accelerators.
Mm-hmm.
The theory for using particle therapy in medicine came from Dr. Wilson again in the 40s of the last century, but we simply did not have the technology to apply them in medicine. Looking at the physics of the dose distribution is absolutely no-brainer. Yeah. So physics understanding was ahead of engineering solutions.
Right.
So we really had to wait. So particle therapy has been used for cancers for maybe 50, 60 years, but research facilities use what we call static beamlines.
Yeah. So they're fixed in direction.
Exactly. So our biggest disadvantage is that you don't get that rotating gantry where you can actually change the orientation of the beam in respects to the patient anatomy. So the patients are also, because these are horizontal beamline, the patient either needs to stand or needs to be sitting in a chair. So they cannot lie on a couch. And the energies of the proton beams to begin with were more at the lower end of the spectrum, maybe 50 to 70 MeV. Mm-hmm. So the first areas where you only need a single fixed beam would be maybe treatment of eye melanomas or ocular cancers.
Okay. And
for those, yes, all you need is a fixed static beamline, a patient sitting in a couch. Mm-hmm. Going back to physics, motion is relative.
Yeah.
So if you have a fixed beamline, potentially you can rotate the patient, which is cheaper to have a rotating chair than a rotating gantry. As I was telling you, the gantry is actually the most expensive part of the proton therapy unit. Mm. But if the patient is only sitting or standing and they cannot lie down, it's maybe, especially if the patient is unwell, it's a solution, but it's not the best patient-orientated clinical solution.
Right.
So it wasn't really until about 30 years ago when the manufacturers had really moved to proton accelerators, which are now cyclotrons or synchrotrons, because we need a different style of accelerators that can accelerate protons to those high energies.
Yeah.
With rotating gantries where the patient is on a couch, And you can again rotate the gantry around a patient and target the cancer for multiple angles. We are not, interestingly enough, so we have like a halfway solution.
Mm-hmm.
We don't have the 360-degree gantries,
Yep.
but we have 180-degree rotating gantries, but we can rotate the couch.
Right.
And then have access to the left or right side part of the body. So we use the combination of both.
Okay.
Rotating the beam and rotating the patient to get the best of both worlds.
So is that's at modern facilities that are being built for this kind of treatment?
Correct.
South Australia is building one right now, isn't it?
South Australia is building one, yes. So the bunker is built. Just to maybe where the costs comes, because the gantry is so heavy, the patient comes into a treatment room that, of course, is height-wise and size-wise, maybe like a smaller lecture hall.
Mm-hmm.
But when you open the door, what's behind, you have the gantry supporting structures and something that we call counterweight.
Mm-hmm.
Imagine you have something that's 100 pounds that's rotating. It needs to have a big concrete or metal block on the other side that's called counterweight to balance it up.
Yeah.
There is like a 3-story building space behind the treatment wall that the patient does not see.
Wow.
It's enormous. So the shielding structure for the Australian Bragg Centre for Proton Therapy is completed. And I can tell you the amount of concrete there would fill in, I believe, 25 full-size Olympic pools.
Wow.
The amount of steel would build a 2-rail train line from Adelaide to Darwin. So, that's why these facilities, in addition to the accelerator itself, are so expensive. So not every city will have one, and we don't need in every city one.
Yeah.
The latest numbers show that you can make this type of facilities cost effective, 1 per every 6 million population.
Okay.
And hence where I was saying Australia could have maybe up to 4.
Okay. This might be a good time to talk about the life cycle of a facility like this.
So if I go to photons, we usually use a photon accelerator for 8 to 10 years, and then we replace it. The photon accelerators by large are very compact. And if you are using the same energy, you don't really have to do any difference to any modification to the bunker. You just bring a new accelerator in and install it, and you can use it for another 10 years. With the proton cyclotrons, because the initial investment is so huge, the life cycle is more something between 30 and 50 years.
Yep.
So that you still use the same shielding, but you will maybe just do a proper maintenance on individual parts of the accelerators. And let's say there is a new, better performing ion source. So you will just replace an ion source.
Right.
Or maybe there are better magnets. So we will install new magnets or, better collimators for the treatment head.
Yeah. So for the proton facilities, really what might be driving replacement of parts is more about the development of new technologies or better approaches. For the linear accelerators, what's shaping the life cycle? Like what's shaping that 10-year period?
Really sort of by how the X-rays are produced, you accelerate the electrons. And then the electrons will hit the target and produce the X-ray cones. So you start having quite a lot of wear and tear in the accelerator. And because the cost of the accelerator is $2 to $3 million, you might start thinking, okay, will I replace a waveguide for $500,000? Will I replace a target for $100,000? which might happen if you need to in the earlier stages.
Mm-hmm.
But also what we do with the accelerators, there is maybe this new image guidance technology. There is new field shaping or radiation shaping devices that we call the multi-leaf collimators. So you might decide it's not economical for me to keep replacing expensive parts.
Yeah.
I can just buy turnkey new accelerator and have all the latest bells and whistles.
Okay.
Yes, I don't want to get into too much details how the technology is evolving. For example, the new accelerators can have even increased dose rates.
Yeah.
Or they have technologies that called breath gating, so that we can actually then irradiate or deliver the radiation only during certain portion of the breathing cycle of a patient.
Okay.
So it's not necessarily the accelerator technology,
Mm-hmm.
but it's the additional, we call it bells and whistles or adds on that make the delivery a bit more sophisticated.
So I'm curious, with these changes in accelerator technology, et cetera, how you go about developing a new treatment protocol for a type of cancer using a facility like this. Like, what would it look like to go from an idea about how to treat a patient with a particular condition to actual clinical practice?
This is one of the most important questions. And the simple answer is it takes a lot of time.
Yeah.
Because, of course, we need to collect evidence that certain protocol works. And that's where we use clinical trial.
Yep.
And trials are exactly what they sound like. It's trial and see. How we usually work with is that we have now 70 years experience with X-rays or photon radiotherapy. That's as our benchmark.
Mm-hmm.
So when we create a proton plan, by large, we try to accommodate, to begin with, the same dose prescriptions as with photon radiotherapy. And we are comparing whether we, at least in clinical trials, getting the same outcomes as with the photon radiotherapy and are not making anything worse.
Right.
So we are always comparing two things. Am I killing the tumor equally efficiently?
Mm-hmm.
And we are looking at something what we call 5-year survival.
Yep.
You know, do I still have 95% of patients, for example, surviving 5 years post-treatment? And then we are also looking at the side effects.
Yeah.
Okay, now that I have used protons, have I reduced side effects related, let's go to the brain cancer, to optical nerve inflammation? Have I reduced side effects? So this data, we start sometimes with smaller case studies on of patients, just to get some indication, but it's not the highest level of evidence. The highest level of evidence needs to start from what we call level 2 to level 3 clinical trials.
Okay.
And then we have to collect patient data for 5 to 10 years to have definitive evidence.
Okay, so let me ask a couple of questions about that. The first is that you talked about side effects. Are you talking across that 10-year period? Is it nearer term? Like,
So the side effects are always multi-level. There will be early side effects and late side effects. So early side effects, for example, even in photon radiotherapy, for breast, could be skin burns.
Yeah.
And you will find them very, very quickly.
Yeah.
Early side effects come with early responding tissues, which is also bone marrow.
Yeah.
So we will be monitoring blood changes in a patient. Again, this is more or less important depending what organ we are we are irradiating. So that can be identified very quickly. Many of these have been eradicated with modern technology. The latest side effects, if going to children and the brain irradiation, the growth development delays, you may not, or later onset of adolescence, you may not find until a few years later on.
Right.
So data collection is extremely important so that we have, information about the early, late, and very late side effects as well.
Right.
And that's where we need national and international collaborations as well. We can pool all the information together. Most of the clinical departments are publishing the results of their clinical data in publications, and the protocols for any clinical trials have to be lodged with clinical trial registries.
Yeah.
So what we can do when we are developing our protocols in Australia, we don't have to reinvent the wheel. We don't have to start from scratch. But we will conduct something that's called systematic review of the published literature.
Yep.
And we compare all the protocols or all the trials that other centers have conducted. Then we perform analysis of the results, and we can then identify which of those protocols provides the strongest evidence for improving the patient outcomes, both in terms of treating cancer and in terms of minimizing the side effects.
Okay. So let's take a step back a bit. And I think there are a few really interesting things from what you've just said that might be worth stepping through. The first is that obviously this is a safety critical thing. You want to get this right if you're going to roll it out across a broad population. And so you start with small numbers and you sort of work up in size as you get a sense of, how safe things are, whether things are working, whether they're achieving the goals that you think that protocol will achieve. Yeah. That's correct? Yeah.
Yes. What we have the big advantage, if I can jump in, we follow lots of the guidelines that are used by pharmaceutical developments. Mm-hmm. But in pharmaceutical developments, I think there is always a bit of blindness because you swallow a little white pill, you don't know what it does.
Yeah.
Some of this blindness is removed in radiotherapy because we actually really understand well how radiation deposits the energy, what the radiation interactions are. So if I generate that treatment plan that I was talking about before with photon versus protons, it's not like we're really experimenting, even if we are starting with small numbers.
Right. That's something we understand very well.
Yes. We immediately see that, okay, I'm not going through optical nerve. I'm not going through brainstem.
Yeah.
I can immediately see, at least in the theoretical dose distribution, how much sparing of normal tissue I am going to perform.
Right.
But of course, maybe I'll just one step back. Before we even go to the patient studies, I don't know whether the listeners like it or not, we also perform in vitro experiment with cell lines in Petri dishes. And we also do small animal experiments, primarily using laboratory mice.
Yep.
We will never get an approval to go to in-human clinical trials unless we show preclinical evidence. Because if the preclinical evidence shows it doesn't work, it will never get approved for in-human trials.
Right. So again, the risk management actually is about starting in cells or animals. And then if that all looks good, then you go, okay, we can start considering humans very carefully.
Exactly.
The other part of this that I thought maybe worth at least mentioning is different countries have different standards with regards to medical treatment and how they're regulated, right? And so your discussion of looking at what has been found in other countries at these facilities and looking at what they've discovered and then adapting that, thinking about how you're going to make use of that in an Australian context. Sounds like it's part of your practice. Is that right?
Yes, yeah, absolutely. Look, in terms of clinical trials, they all publish dosimetry data.
Yep.
So the interaction of protons will be the same in Australia as in Europe as
I
in
would hope
America.
so.
Yes, exactly. So primarily we are after the dose and fractionation. What is it? How much radiation dose per fraction? How many fractions? What is the total dose?
Yeah.
So that's irrespective. Because these facilities are expensive, you usually do have them in countries, maybe more your high income countries, even though we now see the onset of development of these facilities in middle income countries. But most of these have excellent both health and radiation regulations in place.
Yeah.
We also all subscribe to international regulations as published by International Commissions for Radiation Protections, or ICRP, or International Commission for Radiation Units, ICRU. ICRU actually publishes series that inform clinical protocols.
Right.
And also we follow any guidelines by IAEA, International Atomic Energy Agency. So there is some form of uniformity.
Yeah.
Yes. And dosimetry standards are uniform to an extent as well. So, for example, most of our accelerator calibration protocols are referenced to IAEA. But where sometimes the changes come, and that's where the departments might work slightly differently, it comes to the cost of the therapy.
Yeah.
One of the cancers that is very difficult to treat and has unmet demand is pancreatic cancer. And our theoretical studies show that I get a good result when I use 3 proton beams. We are collaborating with a center in Asia, but they are only using 2 proton beams because the patient is charged per beam.
Right. Okay.
So to minimize the cost to a patient, they will be only treating with 2 beams. So that's where some of those differences might come.
Okay.
But that's where we have the trial stage and where we can do lots of things in treatment planning itself without a real patient to identify the dose distributions and the beam arrangements that could lead to the best outcomes.
So you basically have a way of testing in advance what potential trade-offs, if somebody is paying per beam, you're deciding between. Okay.
Yes. Absolutely. So once we have the dose distributions, we have biological models. One is called tumor control probability, which is basically telling me, am I killing enough cancer cells or not?
Yeah.
And the other one is something that's called normal tissue complication probability, where we start thinking, okay, will this person develop this particular side effect?
Yeah. Okay.
So we can, because the radiation simulations are so advanced, and this is, again, thanks to the 100 years of radiation and nuclear physics, we can do lots of things in that simulation domain and prepare the protocols in simulation domain before we even go to real patient treatment.
Does access to trained workforce for these kinds of facilities impact things at all, just out of curiosity?
In radiation therapy, we are not doing at the moment too badly. We have large shortage in nuclear medicine. This is actually another aspect of cancer and other therapies. I was only talking about the 50% of cancer patients receiving radiation for treatment of the disease.
Yeah.
100% of cancer patients will receive some sort of X-ray or radionuclide intervention for imaging and diagnostic purposes.
Right.
So they will definitely have 1 or more CT scans. Many of them will have maybe magnetic resonance imaging, but many of them will have either gamma camera or positron emission tomography or PET scan imaging as well. 100%. So we see a huge development in nuclear medicine, and we have huge shortages in that space at the moment. With photon therapy, we are not doing that badly, but we don't really have a program for proton therapy as much, which is maybe an opportunity space for university.
Okay.
At the moment, what we are doing, look, we don't really have a functional facility at the moment. So it's a bit of a chicken and egg situation. So at the moment, what we do, we send people to train overseas in the facilities that have a well-established program.
Okay.
But eventually we have to implement something locally. I know that professional bodies such as Australasian College of Physical Sciences and Engineers in Medicine or Australian Society for Medical Imaging and Radiotherapy have already starting courses at that professional organizational level rather than at a university undergraduate or postgraduate level. I would be thinking that we might maybe need postgraduate diploma, particle therapy, and make it as an advanced practice to the undergraduate degrees.
Okay, so it's probably the people who have been trained overseas and come back that might be involved in running those programs.
Yes, yeah.
Okay. And what kind of time scale does it look like we will need those on? I mean, the facility is being built now.
So I think some of the people are being trained now because we already, look, while we are not treating patients now, we are sending limited amount of patients overseas, particularly to the United States. How do you decide who to send? So this is where something is performed is the comparative planning that I was talking about.
Yeah.
That this again primarily involves children.
Yeah.
And often with brain cancer, that you create a treatment dosimetry distribution plan with X-rays and treatment dosimetry plan with protons. And you can demonstrate to the select committee that this child will significantly benefit with proton therapy.
Yeah, that makes sense. So it's not like you just like turn the facility on one day and it's all good.
No. There is a huge lead time. Yes.
Let's say when Australia is thinking about these kinds of things, like what kind of lead time are they needing to think about even developing the expertise they need to do the planning to work towards these kinds of major changes to the health?
Look, in Australia, we have been talking about this for 25 to 30 years, and we still do not have a facility. But I would say, depending on what you want to buy these days, maybe 5 years. There are now, especially with companies like IBA or Median, that there are turnkey solutions. And they can already come, okay, this is the accelerator, this is what they can come with a footprint for the facility.
Right.
And shielding recommendations.
Right.
If you are going for something that's maybe going towards carbon therapy and it requires a synchrotron, you might need lead time of 10 years. What we do not have compared to Europe or Japan, because we are not an accelerator country, we don't have inside Australia know-how.
Right.
Couple of carbon proton facilities in Italy and in Austria were based on the know-how coming from CERN.
Right.
Because they have this huge nuclear physics facility that uses the colliders and synchrotrons and everything, you have great accelerator know-how, great engineering know-how, understanding magnets and beam steering and everything. So you can design and fine-tune your own accelerator structure.
Right.
And we don't have that in Australia. So we are more dependent on turnkey solutions, which now do exist, or on collaboration with a company that can design maybe something a bit more a bit more different, especially if you want to maybe increase the energy of the protons than the standard turnkey. Japan is in a similar space because they have Sumitomo, Hitachi. They are building, I think now 4th and then 5th carbon facility.
Yeah.
But they are learning from each of the facility and bringing that know-how to the new facility. Actually, some of the images I saw out of Japan is superconducting synchrotrons. And you can so much reduce the footprint. It's just amazing. So, I don't need diamonds. Give me a new superconducting synchrotrons and I will be so excited.
Nuclear Matters is a production of the Australian National University College of Systems and Society. We acknowledge the traditional owners of the lands on which this podcast is being recorded on or listened to, and pay our respects to their elders and all First Nations people. If you liked what you heard today, please share this episode with friends, family, and colleagues. If you want to send us some feedback on an episode, please email us at nuclearmatterspodcast@anu.edu.au. Keep in mind that this podcast is intended for information and education only. The views and opinions expressed in each episode are those of the individual speakers and do not represent the official policy or position of the Australian National University College of Systems and Society or the university as a whole.